Perfect. So our next speaker today is John Baez, who is a mathematical physicist and professor at UC Irvine. But in May, will be starting a job at
Riverside,
the
Riverside.
university.
I must protest. It's not Irvine, it's Riverside.
Oh my gosh! Thank you so much. I was.
It's okay.
Okay. We start again. John Baez is a mathematical physicist and professor at UC Riverside, and in May will be starting a job at the University of Edinburgh as the Maxwell Fellow of Public Engagement. His blog Visual Insight is gorgeous and widely popular, and his article The Beauty and the Roots. We saw earlier that it inspired Bernat. It also inspired me personally as I was studying visualizations of algebraic numbers, and it fits really within this sort of algebraic starscapes explorations that we've seen a few talks about so far in the seminar. So I've been hoping to have John on the seminar for some time, and I'm really excited to introduce him. So thank you so much. Take it away.
Great, thanks. Let me share my screen here. Um, hope that's hope that's working. So I had a blog for a while called Visual Insight on the AMS website, which is still available, although I'm not still doing it. Um, and the idea behind this blog is based on something I read once from, I can't remember who it was, Sylvester or Cayley, and I can't find the quote right now, but he said that mathematics, in addition to being the study of general patterns, is also the study of interesting individuals. So we all know about things like the circle or the number pi, which are interesting, very important individuals. But there are lots of other individual entities in mathematics that you need to learn about as you explore more and more mathematics. Some examples would be the Mathieu groups or the Golay code or the monster group or Klein's quartic curve and so on and so on. Now, a lot of these entities are hard to draw or visualize, but a lot of them also you can draw or visualize. And that's a really good way to get to know them is to start by just seeing them and then hearing more and more facts about them. So the way I like to think about it is that these individuals are like points and general concepts or general theorems are like lines. So any concept goes through many individuals and applies to many individuals, like a line goes through lots of points. And traditional studies of mathematics, traditional classes in mathematics take that point of view. But there's the other point of view, which is any individual, any interesting individual is like a point and it has lots of lines going through it. And you can also learn mathematics from that way. And it's very interesting to see how different concepts wind up interacting in the same individual. So I'd like to just walk you through a few of these. Now, I am terrible at drawing pictures of any sort electronically. So what this blog did was I would uh, work with other people to draw things and I would explain them. So what I'm good at is words rather than pictures. If I neglect to cite the creators of any picture, I really apologize that they are visible on the blog. So let me just start with an easy one. So there's a good question. If you have an L-shaped hallway, say of width 1, what's the largest possible area of a region that you can move around the corner? So this is called the sofa moving problem because you've probably met the three-dimensional version of this problem where you're trying to move a large piece of furniture through some confined space and you're wondering if it's going to fit or not. So this is a simplified two-dimensional version. And I think it was posed first by a fellow named Hammersley. And Hammersley's solution, which is not the best solution, as it turns out, but his best attempt is called the Hammersley sofa. And you see it here. It's made up out of portions of circles and straight lines. And it has the area, which is this nice number pi over 2 plus 2 over pi. Then later on, people worked on that and a fellow named Joseph Gerver in 1992. I don't know if it's Gerver or Gervais, sorry, found a sofa of larger area, which you can see getting moved around the hallway here. Here it's the object is being kept fixed and the hallway is moving around it. It consists of uh, it's piecewise analytic. So there are formulas for each of these portions of the boundary that are marked out here. Uh, and he conjectured that this was the largest possible area for such a sofa. Um, and recently that has been proved. So in November 2024, Jineon Beck actually proved that Gerver's sofa is actually optimal. So you can read about that. Hammersley published his original conjecture in a paper which I think has the most obnoxious math title of any math paper I've ever read, so I have to read it to you. So it's called On the Enfeeblement of Mathematical Skills by Modern Mathematics and Similar Soft Intellectual Trash in Schools and Universities. And in this rather obnoxious paper, he posed like his problem as an example of like what mathematics should really be. Should be like studying concrete, specific problems. Um, of course, I think that both are interesting and that we don't need to get so nasty about it. um, okay, here's something else. This is called the Golay code. This is not the most informative picture of the Golay code, but this will get you started here. So what we see here are is a rectangle that has 12 rows. Um, each row is a code word. Um, so you're trying to transmit some 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 information, and you're trying to transmit one of these 12 different possibilities. And on the left here, you see they're just you can think of these as zeros and ones, where the ones are the red guys here. And on the left here, just one of them is a one, and the rest are zeros. But all this more complicated stuff on the right are are correction uh, are for error correction. So these ones on the right are chosen in such a way that any two rows of this chart differ by at least 8 places. So if you look at the first and the second row here, you see they differ 1, 2, 3, 4, 5, 6, 7, and 8 different places. So you would have to make 8-bit errors to in transmitting this data to get mixed up about which string of bits you were transmitting. And that's the virtue of the Golay code, that it takes an enormous number of errors to screw up the code. But what is really going on here? What is the principle behind all this complicated error correction stuff? Well, it turns out that there's a very beautiful way to think about it. Here's a picture made by Gerhard Westendorp. So you should think of a icosahedron, and you should draw a bunch of regular pentagons in the icosahedron like this. And when you are trying to transmit one of the 12 possible signals, what you do is you light up um, some of the some of these vertices of the of the icosahedron, and you also light up some of these uh, pentagons, and there are also 12 of these pentagons. So when you light up this vertex here, that is when you make that one of the 12 bits be a 1 rather than a 0, you also light up um, you also light up all sorry, you also light up all these guys that are not on that uh, on that corner, and so you get a choice. Sorry, that are not on that pentagon, and so you get I'm sorry, I'm saying it wrong. When you light up this pentagon, so you think of that as the signal, then you light up the red dots, the red vertices. So that subset of the 12 vertices also gets lit up. This was made by Gerhard Westendorp, and then later Greg Egan made a version that may be helpful because it shows different possibilities of what's going on. So each time one of the pentagons gets lit up, all the vertices that are not lying on that pentagon lit up. And so that's the principle behind the Golay code. You transmit a signal, which is a pentagon, but then you transmit error correction information, which is lighting up some subset of the 12 vertices of the icosahedron that don't lie on that pentagon. And that's the principle that leads to this rather cryptic code here. This code has a lot of mathematical properties. For example, it has a certain symmetry group called the Mathieu group, which is one of the finite simple groups called the sporadic finite simple groups, and it winds up connecting to a lot of beautiful mathematics. So, but it starts out with this rather simple idea of the icosahedron. Okay, on to another tale. So this type of tiling, drawn here by Anton Sherwood, may be familiar to a lot of you. So this disk here is really called the hyperbolic plane. You should think of it actually as extending on infinitely, but we've just compressed it down to a disk, and that's why these heptagons look like they're getting smaller near the edges of the disk. It's just because we've compressed it to fit into our field of view, but in reality, all those heptagons are the same size, and the hyperbolic plane is a non-Euclidean geometry. It's negatively curved, which allows for geometry to go funny in such a way that the angles inside a triangle don't need to add up to 180 degrees. And similarly, you can place stunts like tile the hyperbolic plane with not with hexagons meeting 3 at a corner, but with heptagons meeting 3 at a corner, which is impossible in normal Euclidean geometry. So the study of hyperbolic tilings is much more flexible than the study of tilings of the Euclidean plane. And the tilings of the hyperbolic plane by regular polygons have been deeply studied and are incredibly beautiful and fertile subject of investigation. For example, you can take this tiling here and you can chop out a certain chunk of it, namely a chunk consisting of 24 heptagons. You can take that thing and then you can curl it up, you can fold it up in such a way that it forms a 3-hole torus. And then you get a 3-hole torus tiled by 24 heptagons, each of which meet 3 at each corner. And that is called Klein's quartic curve. Namely, if you put the hyperbolic metric that you got from the hyperbolic plane onto this 3-hole torus, you get a way of putting a hyperbolic metric on the 3-hole torus, which is the maximally symmetric one, which has the largest group of symmetries possible for any hyperbolic metric on a 3-hole torus. And that turns out to have a symmetry group of 336 elements, or 168 if you require the orientation preserving transformations, which winds up connecting it to a lot of other beautiful mathematics. It's an example of what's called a modular curve, and there are many modular curves, and this is one of the good ones to study if you're getting started on the subject of modular curves. Now, I'm interested not only in the 2-dimensional hyperbolic geometry, but in 3-dimensional hyperbolic geometry. So in 3-dimensional hyperbolic geometry, it's easiest to visualize it by sort of pretending you're inside 3-dimensional hyperbolic space and you're looking out, and you can do the 3-dimensional analog of tilings called honeycombs. So for example, in 3-dimensional Euclidean space, you could fill Euclidean space with cubes, but here we're doing something more exotic. So this is called the 633 honeycomb, and Royce Nelson has a whole bunch of beautiful pictures of honeycombs on Wikipedia, hyperbolic honeycombs, these are called. And so what's going on here is first we are tiling a plane with hexagons meeting 3 at each corner. This is actually a Euclidean plane sitting inside hyperbolic space, but because it's sitting inside hyperbolic space, it winds up looking extrinsically curved. And then we have many such planes. And then what we do is that at each vertex here, we actually have not just 3 struts coming out, but a fourth one. The fourth one is going back in away from us, so it's hard to see. But here you can begin to see that they're 4, uh, and so that's the pattern. Each vertex has 4 struts coming out of it, just like like going from the center of a tetrahedron out to its 4 corners, and then each and then and then you get a pattern of hexagons formed by those struts, where 3 hexagons meet at each corner to form a plane. And these planes go off into the distance in this beautiful way here that's only possible in hyperbolic space. This particular honeycomb actually happens to be deeply related to the so-called Eisenstein integers, that is, the complex numbers that form a hexagonal, form a equilateral triangle grid in the complex plane, and you can describe this honeycomb in terms of the geometry of a certain abelian variety that you build starting from the Eisenstein integers. I have some blog articles about how that works. So this leads on to a lot of deeper mathematics. I was interested in this enough that I featured another view of the same thing. So there's another way of viewing 3-dimensional hyperbolic space where you think about it as the upper half of Euclidean space. So if you're familiar with a hyperbolic plane, you may know that there are like several different pictures of the hyperbolic plane. One is the one I showed you inside of a disk, where things get crunched up near the edge of the disk. But another one is the whole upper half plane, where all the crunching up, all the compression happens at the boundary of the plane. And that both of those have analogs in this 3-dimensional case. And so here we're using the upper half space model of 3-dimensional hyperbolic space, and we're drawing a picture of the 633 honeycomb in the upper half space. Again, Royce Nelson is the one drawing this. So here you can see these planes of hexagons a little bit better. These planes, because they are Euclidean planes that are being forced to live in hyperbolic space, they look rather curved and rather funny. If you're familiar with hyperbolic geometry, these planes actually go by the name of horospheres, because sitting in the ball model of hyperbolic space, they actually look like spheres. Although they're intrinsically flat. So this is another picture of the same thing. And I could go on endlessly about these honeycombs and the mathematics that they're connected to, but I will move on to another tale. So this is a kaleidocycle. It's created by someone who goes by the name of Into the Continuum. So what is it? It's a bunch of regular tetrahedra, I guess 8 of them. Each one of them individually is perfectly rigid. They're connected along certain edges, and yet the beauty of it is that they're able to keep moving around in this way without bending each individual tetrahedron. And if you go Into the Continuum's blog, you'll see many pictures of this general sort of moving shapes made by regular tetrahedra stuck together in various kind of ring-like structures. It's an interesting issue because, in a sense, this shape is a polyhedron. the definition of a polyhedron is a much argued question. There are many ways you could define a polyhedron. A convex polyhedron is a fairly well-defined concept, but once you start allowing your polyhedron to be non-convex, then you start asking, can it have holes in it? And could it even look like this? And it turns out that if you have a convex polyhedron, it's rigid in the sense that there's no way to bend it while keeping each face perfectly rigid. So if you imagine the faces is made of being made of an infinitely rigid material, then there's no way to bend the polyhedron. But as soon as you cease, and that's an interesting theorem. I believe it was proved by Cauchy. Yeah, Cauchy claimed to prove it in 1813. Then there was a mistake in his proof, and nobody noticed it for a long time. And then eventually they corrected it. Um, so that's already interesting. But then later on, a fellow named, well, first a fellow named Robert Connolly, and then a fellow named Klaus Steffen found flexible polyhedra that are not convex. And you can click on these links and see motion pictures of how you can bend such polyhedra. But then when you go all the way out and let your polyhedra have holes in them like this, then they can be extremely flexible and do all sorts of interesting things. Okay, on to another tale. So there's a beautiful fact that any cubic surface, any smooth cubic surface contains 27 lines. So what's a cubic surface? Well, it's a surface in three-dimensional space that's defined by a system of cubic equations. This fact that it contains 27 lines is a bit of a tricky fact because when algebraic geometers get into playing with things, they are not content with working with real solutions of polynomial equations. Those behave in a very complicated way. So instead of keeping it real, as the rapper is saying goes, they like to keep it complex. So it's only true if you look at the complex solutions uh, of a complex points of a cubic surface, that is the complex solutions of a bunch of cubic equations, that you can be guaranteed to always see 27 lines. And those are complex lines, which us benighted real people call the complex plane. But for certain particular cubic surfaces, you can actually find all 27 lines in a real picture, which is what we've got here. So this is a very beautiful surface called the Clebsch surface, in which all 27 lines are visible, here drawn in a beautiful motion picture by Greg Egan. And some of these lines intersect in these black points here. The way that you define the Clebsch surface is, well, it's again all this algebraic geometry trickery. Instead of just using complex solutions, they also like to use projective space. So what they do is they would, well, the most symmetrical way to describe what's going on is that you start with five-dimensional space and you write down one linear equation, which is very beautifully symmetrical, which then gets you down to four-dimensional it gets you down to four-dimensional space, and then one cubic equation. And so now you've got a subset, well, really a subset of four-dimensional complex space, but I'm drawing it in C5, but this one equation knocks you down to four dimensions. And then what you do is the projective geometry trick where you count two solutions as the same if one of them is a multiple of another. And these equations are homogeneous, so if any point is a solution, so is any multiple of it. So you count two solutions the same if one's a scalar multiple of each other, and so now you're looking at solutions in what's called projective space. And that's the beautiful, mathematically beautiful way to think about the Clebsch surface. Then to get back to this three-dimensional real picture, you have to fiddle around with some changes of variables, and you wind up getting this rather disgusting cubic equation in 3 variables, but this is what you actually this is what Greg Egan is actually drawing a picture of. So you could read this math at your leisure and see how we get here. There's a huge amount of mathematics connected to this miracle of these 27 lines. That, for example, there's an exceptional Lie algebra called E6, which has a 27-dimensional irreducible representation, which is connected to these 27 lines. And I keep trying to understand that and partially understanding it and partially forgetting it. And I'm sure someday I'll figure all that out. But this is a case of an interesting individual that has a lot of interesting general concepts running through it. Okay, here's another one. This is not quite as canonical of a structure, but it's I think a subject that's worth a lot of investigation. So what would it look like if you were in a perfectly mirrored sphere? Well, I'll tell you, it would look completely dark. That wouldn't be very interesting. So you'd have to have a flashlight in there. So if you shine a flashlight in a perfectly mirrored sphere, what would it look like? I would really love to do that. Somebody should make like a kind of a a museum exhibit where you like have a mirrored sphere with a door in it, and you can like give someone a flashlight and let them walk in it and turn on the flashlight and see what they see. I really don't know exactly what it would look like, but I was very interested. And Refurio Anacro, that's the pseudonym of a friend of mine, made this uh, image. Um, he put a sphere inside a mirrored spheroid. So if you notice this larger thing, it's slightly stretched in the vertical direction. I can't remember why he stretched it that way. The mathematician in me is appalled by the fact that he would work on a more complicated problem like a sphere and a mirrored spheroid instead of a sphere and a mirrored sphere. But maybe there's some really good reason for it, which I forget. But anyway, you imagine that this sphere glows and then you just and shoots out rays in all directions, and then you do ray tracing and see where those rays would hit your eye. If you imagine like you're sitting in front of this or and seeing what you see. And so you'll see lots of mirrored images of this sphere, but infinitely many, and they form these very complex patterns. And I would really love to understand this better. Later, another person I know named John Valentine made a much more elaborate image of this. So here the original ball is here, and it's lit from 3 different directions with soft red and green and blue lights. And I guess he did a ray tracing program that allows for 256 reflections. So we're imagining like an unrealistically good mirror. Uh, and we're seeing all these mirrored images of this sphere. So all these crazy little patterns made by these tiny little, very stretched out ellipsoid-like things, they're all reflections of this original sphere. And as the number of reflections goes to infinity, well, since we only allow 256, this region here gets black. But so this is really wonderful, and I would love to understand it better. And here's a portion of that image. So he made an enormous image file, and this is like a zoom of that. So you can see there's some beautiful geometry going on in here. This doesn't fit on my screen, so I'll just sort of cross through it here. So here we are entering the zone where we need larger and larger numbers of reflections. So sorry. Back to where we were. Yeah. So I urge people to make more images of this type of thing, reflections in mirrored spheres. I'm sure there's a lot to learn there, both just for visual fun, but also mathematical fun. On to another show. This thing is called the Balaban 10 cage. What is this thing? It's a graph. It has a lot of vertices. I forget how many, but its distinguishing feature is that each vertex has 3 edges coming out of it, and the shortest cycles of edges, where you go along edges until you get back to the same vertex, have length 10. So all the shortest cycles have length 10, and every vertex has three nearest neighbors. Balaban was working as a famous graph theorist. He was working on chemistry mainly at the time when he came up with this thing. He had been thinking about cages. So you could talk about an RG cage where every vertex has R neighbors and the shortest cycles have length G. And here are some. Okay, so this is, I'm only going to do three G cages. So here's the three cage. The shortest cycles have length 3. That's a friend, our regular tetrahedron. Here is the 3-4 cage. This is famous if you know graph theory. This is like one of the minimal graphs that you can't draw in the plane without crossing things. If you've heard that story about people with electrical lines and gas lines and trying to get them to trying to show that you can't get them to run all these lines without them crossing on the plane, that you run into K33 as well as K4. But then the only 3-5 cage is this more beautiful graph here called the Peterson graph. Here you can see these cycles of length 5, these pentagons, or that star in the middle. Here's the only 3-6 cage. It's called the Hewood graph, so you can see these cycles of length 6 showing up. Here's the 3-7 cage, the only one. It's called the McGee graph. You can see cycles of length 7 if you can count fast enough. And here's the 3-8 cage, the Tuta-Coxeter graph. Then there turned out to be 18 different 3-9 cages, and Balaban was trying to understand and create a 3-10 cage. And there are now later 2 more were discovered, but the first is named after him, and it's this one here. I do not know many beautiful mathematical facts about this Balaban 10 cage. I suspect that there must be beautiful mathematical facts to be seen about it. But that's an open mathematical question as far as I'm concerned. Maybe someone has found some, but I've looked and I haven't found any. So we could find some if we look for something a little bit simpler. Here's the McGee graph. So this is the unique 3-7 cage. It's 3-colorable, which is why it has these 3 colors here. So it's drawn here by someone by the name of Coco90 on WikiCommons in such a way that no vertex has the same color as any vertex that's connected to it by an edge, and you need 3 colors for that. Now, I got interested in trying to understand the mathematics of this one to see if there's like any deeper mathematics behind this thing. And so I read on Wikipedia or somewhere that this has a symmetry group of order 32. And I love groups, and groups are often a way to understand what's really going on behind these symmetrical looking structures. Unfortunately, there are a lot of groups of order 32. And then well, here's one of the symmetries, by the way. Let me just show you a beautiful symmetry. So there's this beautiful movie, I think also on WikiCommons. This is the McGee graph, where the vertices are drawn as these balls and the edges are drawn as these arcs, some of which are very beautifully curved. And what's going on here is it's executing a symmetry. So this little apparatus has to go around twice before a vertex gets back to its original location. So although you see a sort of 4-fold symmetry of this picture, it actually isn't. It's executing an 8-fold symmetry that it has to go around. Each vertex sort of trades its place with another vertex 8 times before it gets back to where it starts. But the total symmetry group has 32 elements, so this is just 8 of the elements, so it's not the whole thing. And so I was trying to understand this, and I don't even remember the story, but somehow or other, I could click on this link, but I won't. Gordon Royal told the world that which of the various 32 element groups is the symmetry group of this graph. It's the 43rd one, according to some numbering system. And so I looked up that 43rd one, and I learned what it was. And the easy way to understand what it was is that you take the line, but it's the line with 8 elements. So you look at the integers mod 8, and you think of the integers mod 8 as forming a line, and then you think of the transformations of the line that are of these so-called affine transformations like ax plus b, which are invertible, and that's the symmetry group of the McGee graph. Now, for transformations of the form ax plus b to be invertible, we need the number a to have an inverse, but not every non-zero element of Z mod 8 is invertible. Z mod 8 is not a field, so the only invertible elements in Z mod 8 are 1, 3, 5, and 7. So the transformations that we get here are the ones where x goes to ax plus b, where a is 1, 3, 5, or 7. And that was sort of the key to trying to understand the structure of the McGee graph in a better way. And basically, it turns out that you can build the McGee graph by thinking about this line over Z mod 8. And you can think of the red vertices in the McGee graph in this picture as the points in that line. So there are 8 of them. But what are the blue vertices? Well, that is a much more tricky story, and I will not attempt to explain it here, but Greg Egan and I worked out a description in terms of the geometry of the line, what these blue things are. Notice that each blue thing is friends with exactly one red thing. And each red thing is friends with exactly 2 blue things. So you need to think about what you have the points on this line over Z mod 8, and then you need to come up with something else such that there are 2 of those things that are friends with any point. And each point is friends with only one. And each of them is friends with only one point. Yeah. I may have said that wrong, but in the pictures here. So Greg Egan eventually cracked the puzzle. I'm hoping there's still a more beautiful solution to the puzzle. That is like a beautiful geometrical description of the McGee graph. And hopefully, if one got good enough at that, one could maybe go ahead and try more complicated cages, and maybe there's some beautiful geometrical description of the Balaban cage. Well, I will stop here. There are an infinite number of structures that are even beautiful ones, I claim, in mathematics, but there's certainly not an infinite amount of time to talk about them, so I better stop. So thanks very much.
Thank you so much, John. I wanted to open the floor to some questions if anybody would like to ask any questions. I suppose think you're able to unmute yourself, so could hop in or post things in the chat or in Discord if you'd like.
Yes, I'm now looking at the chat finally, and yes, I think that is the same Klepsch, which is really interesting, as the famous Klepsch-Gordon. And I did not know this fact that Matthew Macaulay just told us about this particular group. So I will ponder that fact, Matthew, and I will try to understand if I can see that it has any manifestation for the McGee graph, because it's. So I was thinking about the symmetry group of the McGee graph, and now you're thinking about the symmetry group of the symmetry group of the McGee graph, which is a little mind-blowing. That is, it'd be really interesting if you could. So that means that, like, if I have any symmetry of the McGee graph, you can apply this outer automorphism to it and get a different symmetry of the McGee graph. And yet it acts trivially on conjugacy classes so that we get a new symmetry that's conjugate to the original one. So maybe I could eventually visualize that. But I would love questions. I'm just blabbing until I hear a question, but that's probably a bad idea.
I do have a question. I guess I've tried my hand at illustrating the 27 lines on the cubic, and I feel like there's two main problems. That one you mentioned was like some of these lines can be complex. You could Klept gives you a great one where all the lines are can be real and easy to see. But I'm wondering more broadly, like another problem that can arise is also the lines can be very far apart or like near infinity in projective space or something like that, um, which makes it hard to illustrate. I'm wondering if you know of any like choices you can make to not just have like all the lines be real, but also like close enough to the origin to see.
I don't know anything good about that. Were you working with surfaces other than the Klipsch
Yeah, I
surface?
was trying to think about it as like, because if you pick 6 points in like the plane, you can kind of get a cubic surface that way by blowing them up, and that guarantees they're real if you pick 6 real points in the plane.
I see.
But then they ended up far apart. I'm just not sure. I figured
That's a
I'd ask.
good, yeah, no, I'm sorry, I have no insight into that. So that I don't even know. So do you get all the possible options for cubics where all the lines are real by the procedure that you described?
So any possible cubic surface can be constructed by blowing up 6 points on the plane.
Mm-hmm.
And then you can guarantee that they're real if you blow up real points. But it is a good question that um, can you, is the converse true?
Uh-huh.
How can you
Okay.
classify all the ones whose lines are real? I don't know the answer to that.
Yeah, I don't know. It's just naturally interesting question. Someone in the chat, namely Aaron, asks if you know which 6 points give you the Kleps surface.
Um,
I don't know that, but you might
I'd have to
know
think
that. Yeah,
about it. I
yeah.
think if you think about the plane as P2, I think it's like the most symmetric choice you can make with like ones and zeros. But I'm not
Uh-huh.
100% sure.
Hmm. Yeah, that's interesting. There is there is a beautiful book whose name I forget, but which is listed in my blog article about the lines on a cubic surface. And it's such a rich and complicated subject that I got scared to start studying it because I felt that I might like while away the whole rest of my life because there are many configurations of lines and so on with like uh, it goes on and on.
Yeah.
So yeah, it would be very nice to do something where you like took the Klepp's surface and started deforming it in such a way that all the lines stayed real.
Yeah, yes, I agree. And that would be
Uh-huh.
cool. I mean, like, yeah, in response to Aaron's question, I suppose if you could like identify which 6 points they are, then if you could like deform it
Start
by just moving one of those 6 points, that should happen.
Yeah, that should definitely work. Or move them in some symmetrical way or whatever you want.
Yeah.
Yeah. Yeah. Fun fun challenges here for those of you who are able to do the math and also make the videos.
We ask a question here? Yeah, where's the microphone? I don't know, just speak. Yeah,
Hi.
so about the, like you mentioned at some point, like the rigidity of convex, polytopes. Is this specifically for 3 dimensions? Like I'm thinking I can tell it's not true for 2 dimensions, but then what about for greater than 3 dimensions?
That's a I'm forgetting what I knew about that. People have studied it and they know a bit about 4 dimensions. If you send me an email, I can say something about that, but I don't remember now. Sorry.
Uh,
Yeah, that's a
uh,
great question. I just don't remember that would be really neat if it wasn't true in 4 dimensions.
can I share screen very briefly?
Yes. So just the picture John showed of the 3/8 cage reminded me of a picture that a student of mine once made. I hope you can see it. And this is an illustration that the trefoil knot is fibered. I'm not going to explain why because it's not my talk. I just wanted to mention it exists. The student is Jesse Betancourt, and it's very similar to some animations that John was showing. And I'll stop the share at this point.
Nice. Yeah, that's interesting.
So that thing that George just said, and also Gabriel's comment earlier reminded me of something this is like kind of a soft question, but it feels to me like a commonality of most of the things that you described in this talk, like maybe basically everything except the sofa, is that they're all highly symmetric objects. And I was curious about whether that's like a intentional part of your curation, or there's some sort of deeper thing that made these especially interesting to you for some other reason.
I definitely wanted visually striking images. The graphs aren't actually so incredibly visually striking there, but except for their symmetry. But I have to just admit that I'm a huge fan of group theory, so it just probably sort of infiltrates my thinking. Yeah, whether I want it or not. Yeah. Yeah, so I mean, the great thing about group theory is, right, that if you have two different structures that have the same symmetry group, then they all of a sudden you can transfer information about things from one of them to the other, so that it links radically different structures. So maybe that's one sense in which it's a bridge. You could sort of think of it as like proto-category theory. Uh, I mean, a group is a very nice little category with one object and everything invertible. And you can find such categories hiding inside all sorts of other categories. And so they just link mathematical structures. So that's, I guess, my explanation of why it happens so much.
That does make a lot of sense. I mean, it shows up explicitly in your discussion of that graph, the 310
Yeah.
gauge.
Yeah.
And I guess it also potentially, do you know if that's how they discovered this presentation of the Golay code?
I do not know how they discovered that presentation of the Golay code. It could be connected to, for all I know, that was discovered by Conway with his, because I think he has, yeah, he has found some beautiful connections between them. Some of the Mathieu groups and the icosahedron, if you look at the sphere packing lattices and groups. So here's a cool thing. So if you take a ball and you can put 12 balls around a ball that all touch it, and those balls, you can locate them at the vertices of an icosahedron, but you don't have to. So it turns out that those 12 balls don't actually touch each other. There's a little bit of room between them. And so you can roll those balls around on the surface of the central ball. And Conway asked, like, what's the symmetry group? What symmetry, what permutations of these 12 balls can you accomplish by rolling them around? And so, of course, you get the symmetries of the icosahedron, but you can get more. And he shows that it's a Mathieu group. I think it's the Mathieu group M12. So that's I think winds up being connected to the stuff that I'm talking about in some way that's too deep for me to understand right now, but it's really amazing.
That's cool.
That's a very Conway-esque discovery, isn't it?
Yeah.
It's nice to see you, Aaron, in person. I don't know if we ever actually met, but
Oh, yes, we did meet briefly, but also I I did get your email or the email from that other student a while ago, and I was just thinking today I need to respond to it finally. Right? So I will do that hopefully this afternoon.
Don't worry. Yeah.
I appreciated getting the email. That was really cool to see.
Great.
I think there's more
Hello.
questions in the chat,
That's
by the way.
Yeah, I'm not seeing it. I'm not on the Discord, so if I may go
Ah.
there afterwards, and I'm not. I think I would need to. I would need to join this. It'll take me a little while to get into that Discord. So I think maybe you just rotated
Yeah.
90 degrees, Aaron. That's a very disconcerting.
That is. Sorry, so this was in the Zoom chat, Glenn Whitney asked about 3D presentations of these cage graphs.
Oh, I see. Neat.
Okay, well maybe there was a reply to that as well. So someone Daniel Piker has given a link in response to Glenn's question, so maybe we can check that out. I think we should wrap up for now.
Sure.
The Zoom. Thank you all. Thanks to the speakers. Very lovely presentations today, as usual. Thank you very much. Thanks to all the participants for showing up. And again, if anyone would like to present a show and ask, a 5-minute presentation to open up one of our monthly sessions, please let us know, sign up on the form, and we will get you on the schedule. We have slots available. And I think that's a wrap. I'm going to stop the recording, and feel free to continue conversations and other things on the Discord. Thanks, everybody.
Great. Thanks. Bye.